Hi, my name is Monika. I will present Micromax, which is a beamline at Maxwell Laboratory that can do SSX and time-resolved crystallography. So first, very briefly, what is MAX4? So it's a big synchrotron facility in Sweden, located in Lund. It's 40 minutes by train from Copenhagen, so it's very close to Copenhagen. We have LINAC that gives us our accelerator beam, and we have two rings. One is at 1.5 GeV and the big ring is at 3 GeV. The two MX beamlines, Micromax and Biomax, are located on the big ring. So Micromax, why did we build another beamline if we already had one MX beamline? The reason was that we wanted to do more challenging samples and we wanted to focus on serial crystallography. Since Biomax, when it was built, serial crystallography kinda didn't exist yet. So it wasn't designed to do anything more than a simple fixed target and a very complicated way of doing HV. And we wanted to do more time-resolved experiments since the field was moving more to study dynamics. So what we can do at Micromax is then we can do standard crystallography. We can also do room temperature studies, a plethora of serial crystallography experiments. I will show everything that we have done so far and what will also be possible later. Time-resolved and fragment screening will be, time-resolved is used now. The fragment screening is coming up in next year. We just recently hired a postdoc that is going to work on that. And also we left space for new methods that are going to be developed down the future that we can implement that in the beamline. The reason for that is that that's why we have actually two hutches. So we have hutch 1 where current experiments are happening, and everything that we have done since we started with user operation last year has been done in hutch 1. Hutch 2 currently is just offline setup in laser lab, but the idea is that in hutch 1 we have standard crystallography and kind of standardized cellular experiments, while hutch 2 is going to be more like DIY Lego build your own setup. So if you have a unique idea, or we are actually thinking of putting the tape drive in hutch 2, or if you come up with something completely crazy you want to test out, that's going to be possible to do in hutch 2. Important note is that while hutch 1 is operation, hutch 2 cannot get beam. We literally will have tube going directly through here. So only one hutch at a time can have beam. But while we are doing stuff in hutch 1 with the beam, we can do spectroscopy and other stuff with the laser if it's not required in hutch 1 in hutch 2. This is like very nice cat picture, how stuff looks like in hutch, in the hutch 1. It has few differences compared to Biomax. One of them is that we have two monochromators, so we have DCM and MLM. We can get with DCM to the flux of 10 to the power of 14 and with MLM to 10 to the power of 15 photons per second. Currently our beam size is 14 by 14 microns, but we are installing extra mirrors this summer, which will enable that we can go down to the 1 micron in size beam. We have two detectors. One is the Eiger, the other is Jungfrau. Both are 9M. We also have, as you can see here, a sample changer, which is much bigger than the Biomax one, so we'll be able to do much faster high throughput. And a lot of different sample deliveries for serial crystallography, which I will get to in a bit later. So I already mentioned some of the things that we have, but this is currently how the hutch looks like. So we have a very big detector table that can hoist two different detectors, and it's very cool to see how they move in unison when we need to put one in, and when we need to put the other one slots back. Our sample changer is also on the rails, so if we are not doing anything with pucks, it moves back, so that this part here, we have a lot of space that we can enter and be close to the sample. So if we need to install pumps or if we need to do any troubleshooting during the data collection, that we have enough space and we are in no collision with the sample changer itself. The current Jungfrau that we have, it's not ours, it's on loan from PSI, but we are getting our own in January next year. Okay. Well, since we are doing time-resolved, we also need our own laser. We have XPLAT NT. We chose that one because it has the highest wavelength coverage, because when we asked our users what wavelengths are you interested in, we got a very big range, so this made most sense. The pulse width is 2 nanoseconds, and it can be a repetition rate between 1 and 20 kilohertz. And as I said, currently that is set up in Hutch 2, which we kindly call a bat cave, because usually Manoop, who works with spectroscopy, does everything in dark there. But these are current pictures, how stuff looks like inside. We can also measure some stuff that is not necessarily crystals. We can measure solutions, and we can also measure it in cryo conditions. As you can see here, we have the cryostream installed. This was something we measured a few weeks ago, a sample from an Amsterdam user that was loaded here inside the glass cuvettes, and then we could measure and see the change that they were interested in once the laser was exposed. The control system, I think almost all the beamlines in Europe are using MX-Cube. We have our own version too. All the data also goes to ISPy-B and XC, and we have our customized version for the SSX experiments, both for injector and for fixed targets, since they require different things that we need. We also have a pipeline in development. Currently, how it looks is that during the data collection, we are getting live indexing from doser spots. So this shows every 100 image live on screen. We have the live doser results, which are showing for every image how many hits were in the image, what is the doser score, and roughly what is the resolution. After each collection is finished, we get data out that tells us how many percentage of images were indexed and how many were not. And we also get the heat map. Here you can see we were deliberately collecting on a part of a chip where only diffraction was only in a corner, so to confirm that we actually do see properly the heat map. Down the line, we will also have down the line idea for the pipeline is you come, you collect, and you leave with the MTZ file. So that we know that you need to do a lot of processing later a bit yourself, but that you can see certain results where you're at the beamline. So if you see, oh, I need 10,000 more images to get my data to look better, we can now know that on the fly and adjust, which is actually something we did 3 weeks ago when we properly used the pipeline fully for the first time. We saw that the set that users were collecting was not fully done yet, so we needed to collect 2 more chips, and then it was done so we could continue with the next collection. Why is this not working? Okay, so sample deliveries that we have. We kind of went with the motto that we need to collect them all. I think except tape drive, there isn't a method that we aren't using. So we kind of categorize them in 3 different categories. So a single crystal / plate, fixed target experiments, which we have 2 different support systems, and flow devices. And I will quickly go through all of them. So for the HV injector, it's a high viscosity extruded injector. We have our own custom made from Heidelberg. We can have 50, 75, and 100 micron capillaries used, and the reservoir is 330 microliters. Just to give you a perspective how that can go if we are running at the fastest rate, which is 2 kilohertz, the reservoir is emptied in 27 minutes. If we are going very slow, it can last for 3 hours. So it depends on your experiment how fast we need to change it. It has its own custom holder for the goniometer. And because the reservoir itself is encapsed, it is also very nice for light-sensitive samples because you can prepare it in the lab, which is also equipped for light-sensitive samples, and then without any fear, bring it to the hutch. The hutch also can be converted into a dark hutch and also have appropriate lighting, which this is a picture from last year in December when we were doing data collection for a sample that could be in red light. So the whole hutch was then in red. And since we also have an IR camera on our goniometer, we could actually then see the sample before we start the data collection, so we are not completely working in darkness. Serialax flow cell, you already heard about that. That was something that was developed together with the Gothenburg University, so it's another way how to deliver viscous samples in front of the beam. It's much easier in a sense that you don't have to then transfer it from the Hamilton syringe inside HV. You can just directly connect the Hamilton syringe. And unlike HV that sometimes has a problem that you have curling of the sample, since this is going through a thin glass capillary and you're shooting through the capillary, you don't have any curling problems. You do have slightly higher background, but then that's why you need to choose which method fits best for you. And that's why we didn't want to choose as a beamline what you can have both if you want. Another thing that we are developing together with KTH is we have 2 things that are for viscous samples, but We didn't have anything that is for samples in solution. So that's where acouphluistic comes in. We are doing focusing with acoustics. This I cannot show results yet because the paper is in submission, but this is how the setup looks like. So we use ebb and flow pumps to flow. The sample is in this DIY anti-settler, and we have a flow monitor so that we know how fast we are flowing. And this is where the chip itself is. The piezos that give acoustics are positioned here, and down here on the table is what controls them. This is how the data collection looks like when we start. So you can see slightly here how the focusing is looking, and then how, so the sample is here, the detector gets activated, then we can do data collection, and no sound. And just to focus on that, you can see how a sample is directly focused in the center of the capillary. And we did collection without focusing and with focusing, and we showed, which you will be able to see in the paper when it's published, how better it is with focusing, because we also reduced the amount of sample that it's needed and the burning that we get, which is a normal problem when you have samples which are not in viscous material. So moving to the fixed targets, we have 6 different fixed targets that you can use. Again, you don't have to choose, you can use any that you want. 2 of them, the serial X and mitogen, are also compatible with our sample changer, so you can prepare them beforehand, load them on the puck, and then you don't have to go inside the hutch and change each manually. And also serial X, mitogen, and Excel tool can be put in cryo conditions. So you can collect also in lower temperature if that's something that you wish for. One example where we also recently used serial X was we did cryo trapping with Dr. Olga from Amsterdam with orange carotenoid protein. So our setup, we could very nicely bring our nanosecond laser and shine to their setup. They needed to cool the crystal at -30 degrees and then shine it for 1 hour with the laser before we could do data collection. This is when we were just aligning the laser to see that it's on the whole chip. So one thing that we also have with this type of laser is that we can have big spot and also small spot, because this is 5 millimeters in size, so it's a quite big chip. We will also have the SSX head. Currently it's being commissioned. It will be operational for users in 3rd quarter of next year. Currently we are being commissioned, almost done, yes. Another thing that you need is sample preparation lab, so that you can actually come and prepare your sample. We have 2 different labs. One is the preparation lab, which is also equipped, as I said, for light sensitive experiments. We can have both red, green, and blue, depending what you need. We also have a humidity box if you need to prepare samples that are maybe sensitive to dehydration. We also have environmental lab. This is where we have our offline injector setup, where we test samples before you bring them to the beam. And we also have 2 different microscopes which can help in identifying both crystals and the setup. On the Keyens, for instance, we can load that acoustic chip, and then with the microscope follow if everything is working correctly before we load it to the beam, which also helps to avoid certain problems that will happen before it goes to the beam, so we don't lose beam time. Why we also have offline setup for testing. This is something we did a few weeks ago for users that are coming in 2 weeks. And that is to optimize how the stream is going. So the first video is what we don't want the stream to look like. This is curling, and this is absolutely horrible to collect. And that's why it's necessary that we can optimize how the stream is going to be before you come and collect, because this is how you want it actually to look like. And just to finish up, so different support that we offer is that every other Tuesday we have crystal testing. And regardless if you have or don't have a proposal, you can send crystals to be tested to see is that compatible of what you want from a beamline. We also offer support for offline testing and sample manipulation, one being the video that I just showed. Also support in experimental planning. If you don't know how to do anything, but you know, I want to see this, we can sit down with you and plan everything. Of course, support during the actual beam time, and full support with data processing during and after beam time, and with any labs and extra equipment that is necessary. And if you need to apply for a beam time, all the information is here and also available on Max4 website. This is our current group, which we are lacking a picture because we need a new picture, but this is our current group. Micromax team is a bit bigger because, well, time-result experiments require more people on site to work on. And I want to thank all the founders, especially Novo Nordisk, because of them we were able to build the beamline in the first place. Thank you for your attention.